Hello everybody, thank you for tuning into this talk, the topic of which is exploring the latest and greatest from Java 14. My name is Miro Cupak, I'm with a Toronto-based company called DNA Stack. Our mission at DNA Stack is to improve lives of people affected by genetic disease, and we do it by making standards and technologies for discovery, sharing, and analysis of biomedical data. If health tech is something you're interested in or curious about in general, feel free to reach out to me. I'm very passionate about this topic and always happy to connect and talk about it. If you want to reach out, here's my Twitter handle in the corner here. In this session, we're not focusing on genetics or healthcare. We're focusing on the underlying technology stack, which of course, in our case, is Java. The title of this talk narrows it down to what's new in Java 14, which is the latest GA release at the time of recording this talk. But of course, Java 15 is just around the corner, and I think it really would be a shame not to cover truly the latest and greatest. So I thought it would be a good idea to actually extend this topic and not only cover Java 14, but also touch on some of the key features coming soon in Java 15. So what are the features we're going to talk about? Well, interestingly enough, a big focus of Java this year have been new language features, particularly developer productivity language features coming out of Project Amber, as opposed to, for example, library APIs and tools, which as users and consumers of the JDK is where we typically get the most visible updates. That's interesting and very impactful, because even though the changes in themselves are relatively small, because they're at the language level, they affect every single developer. So we're going to do sort of an introductory high-level overview of what I think are the most impactful features in Java 14 and 15. To be more specific, we'll take a look at switch expressions, pattern matching for instanceof, text blocks, records, sealed classes, as well as a couple of new APIs, specifically flight recorder and foreign memory access. Now, before we go any further, there's one thing you should know about me. I'm bad at making slides. So I've prepared exactly 4 slides for you today, and you've seen 2 of them, and this is the third one. And as this slide suggests, the rest of this talk is going to be pretty much a live demo. I like learning through examples, so I'm going to write a lot of them. And I'm going to write them in JShell, because I find it's nicer for demonstrating sort of isolated things when you want to abstract away from all the magic that IDEs do for us. So let me switch to my terminal here, and let's take a look at the first feature. So let's dive right in and start with the first productivity language feature from Project Amber, and this feature is switch expressions. Switch expressions were a preview feature in Java 12 and 13, and they're a full permanent feature since March this year and its Java 14 release. Preview features, if you don't know, are features that are implemented as part of the JDK, but may not be permanent. So the goal is basically to give developers access to these features to test them in practice before committing to maintaining backwards compatibility forever. In other words, preview features are to the language and to the VM what incubator modules are to APIs. Don't worry, they're not available by default. You have to pass a special flag to the compiler and the launcher to be able to use them. In fact, we can see it here. If I could take a look at my environment, you can see that I'm giving JShell this enable preview flag, and that gives me access to preview features. I don't need this for switch expressions in particular. They are a permanent feature enabled by default now, but I wanted to introduce the concept because some of the features that we're covering today are still in the preview state. So if you want to try them out as we go, this is the flag you will need. Switch expressions is essentially an extension to the switch statement so that it works also as an expression. This also addresses 2 other slightly annoying aspects of traditional switch. The default scoping of switch blocks, the block is treated as like a single scope, and the default control flow behavior, this sort of fall through of switch blocks and having to use breaks everywhere. This is basically done by introducing switch labels that kind of resemble lambdas. So let me just start by declaring a variable I'll be switching on. Let's call it x. And now we can make a simple switch expression on our variable x. And I'm just going to do something really simple. If this is 0, return 0. Otherwise, return 1. So kind of a simple Boolean simulation here for demonstration purposes. But you can see a few interesting things here already. First of all, this returns 0. So the output of the first part without using any breaks. We're only using expressions inside rather than statements, right? And this whole thing is an expression because it has a return value. There's also a convenience aspect to this. This syntax is very concise and we can even aggregate multiple cases. For example, if I wanted to say if this is 0 or 1, return 0, otherwise return 1, I can just do it easily like this. I mentioned that this new syntax works for both expressions and statements. So if I actually wanted to use a statement here, let me simplify this switch a little bit more just so that I don't have to type that much. I'm just going to leave a single branch here. I'm going to type some statement, maybe just print line, hello, and this is a simple switch statement. So you can see that there's no return value this time, but it did correctly print hello. We can, of course, execute statements and still have an expression with a return value by using blocks, so kind of a similar approach to lambdas. If I wanted to take advantage of this, all I need to do is wrap this in a block, and then I can use the new keyword here, keyword yield, to return a value, something like this. And you can see now that the value was returned, and we also got the printout from our statement here. I say yield is a keyword. Strictly speaking, it's not a keyword. It's actually a reserved type name. And what that means essentially is that it doesn't conflict with things that keywords normally conflict with, such as variable names. In other words, I can do something like this. I can declare a new variable here, and I can call it yield. And let's say this is hello. And then I can yield this yield variable here, and this is going to work just fine. Now, it's certainly not a practice that I would recommend from the perspective of writing clean code, but it does work. A note here, switch expressions must be exhaustive. In other words, for all the possible values, there must be a matching switch label. That's not the case for switch statements, of course. In practice, this means that you need to specify the default clause, like we've done here. There's an exception to this rule. If you're switching on an enum and you cover all the values, the compiler will insert the default clause for you, which is convenient. This brings us to the second productivity feature, again, out of Project Ember, which is pattern matching for instanceof. This is a new preview feature in Java 14 and 15, so it will likely be permanent in Java 16. It hasn't been officially listed with this target at the time of recording this talk, and it's not enabled by default in the early access builds as of right now, but it has been noted on the mailing list, so it should be happening. The goal of this feature is to simplify one very common situation we have in our code. We often have some sort of a logic that combines testing if an expression has a certain type, and then conditionally extracting components of its state for further processing. What I'm sure each one of us has written many times before, and probably auto-generated many times too, in the form of equals and hash code, is the instance of and cast idiom. So let's start here by constructing an object. Let's call it O, and let's assign some subtype to it. Let's say a string. Now, in order to process this object, what we would normally do is first test if this object is a string, maybe something like this, O instance of string. And then if that is the case, I'm going to cast this O to string. Let's say string s, and a quick cast here. And now I'm going to do something with this object. Maybe let's just check if this string is empty. And this, of course, works, but the problem really is the boilerplate here. This is tedious to write. Most of the time after you type a test, you follow up with a cast so that you can do something with your object. And it's also verbose. The type, string in our case, is here 3 times, right? Which obfuscates information and creates opportunity for error. The proposal is for Java to introduce pattern matching, similarly to other languages like Scala. Pattern, in this case, is a combination of a predicate that can be applied to a target and a set of binding variables that are extracted from the target only if the predicate is satisfied. In the case of the instance of operator, this means extending the operator to not only take type, but also a type test pattern. In other words, a predicate that specifies a type and a single binding variable. For example, with this new feature, I can rewrite my previous example like this. I'm going to completely remove the cast here. I'm going to add a binding variable at the end here. And you can see that this works nice and easy. So the way this works is the instance of operator matches the target O to the type test pattern like this. If O is an instance of string, then it is cast to a string and assigned to the binding variable s, which is just a little bit shorter, nicer, and less error prone. Of course, this is not super significant, but since we type and read such code all the time, it could actually have noticeable compound benefit over time. But what's cool is that now we can simplify our code even more and take advantage of the lazy nature of the AND operator. And I could just rewrite this like this. I'm going to remove all the extra brackets. I'm just going to use AND here, and let's get rid of this if completely. And you can see that this works as well, nice and easy. and this time without any casts, so not risking any runtime errors. One thing to note here is the scope of the binding variable, s in our case. If we go back to our example here, obviously you can only cast this O to string if the test passes, right? If instanceof evaluates to true. So if we add another branch here, if we do an else, and then we try to do something with the string here, maybe just, it's empty like this, you can see that this won't work. S simply doesn't exist in this scope. And this is something that will be checked compile time, which is pretty nice. Well, this is kind of intuitive and allows us to safely reuse pattern variables, for example, across multiple checks. This flow scoping does come at a cost. And the cost in this case is rather unfortunate interaction of the flow scoping with shadowing of fields. In other words, if your variables have conflicting names, it's pretty easy to introduce a bug. For example, if I already had a variable as defined, let's say I'm going to create a new one here, and now if I type the code which previously did not compile, you can see that now it would, in fact, compile without issues. Because as in the first branch here of our if statement is the pattern variable, right, as expected. But as in the second branch is now our original variable from before, not the pattern variable. So take advantage of this feature, but be careful when it comes to shadowing. Another feature that came out of Project Ember here are text blocks. Text blocks are still a preview feature in Java 14, but permanent as of Java 15. And they are essentially multi-line string literals where you don't need to escape most things. And they sort of automatically format strings in a predictable way with you having control over the formatting. In other words, this is perfect for cases where you need to include source code in your program in a string literal, like an SQL statement or JSON would probably be pretty frequently used, maybe even HTML with some frameworks. That used to be pretty painful, right? Usually when you want to copy SQL or JSON to Java, there's a significant editing step involving escaping it correctly, particularly quotation marks and things like that. And then it's not readable, and as such, it's hard to change and maintain. And that's what text blocks address. So it's a new kind of literal in Java, enclosed in triple quotation marks so as not to conflict with existing constructs. For example, I could create a very simple JSON here, maybe something like this, just a simple foo bar, and let's close the JSON, and let's close the text block. Notice a few things here. The text block is equivalent to the string literal printed here, and the whitespace is preserved, including new lines. You can specify them explicitly, but you don't need to. You also don't need to escape things either, particularly the quotes. But notice what's actually the content of this text block when you compare it to the string here. The content starts on line 2, just after the first 3 quotes, and it ends just before the final 3 quotes. There's a new line at the end here. This is typically what you want with source code. If you didn't want the new line, this is how you would need to put it. You would need to put these triple quotation marks right here, and now you don't have a new line at the end. Similarly, if I do something like this is not an empty string, right? This, in fact, does not compile. This would be an empty string, which obviously is not very practical. Don't make an empty string that way, but that's how it works. I mentioned that text blocks preserve formatting, but that's not entirely true. They do a couple more tricks convenient for storing code. For example, they remove trailing whitespace because that you typically don't want in a program. So if I go back to my text block here, and if I add some white space at the end, you can see that that white space is stripped away. If you're not happy with this default behavior, you can use one of the special escape sequences here. For example, I can escape the last space here, and now you can see that the white space is stored correctly. Alternatively, I could suppress the new line, so your spaces will effectively be in the middle of the line now. Text blocks also remove common whitespace prefix at the beginning of each line to be sort of indentation and IDE formatting friendly. So for example, if I indent everything, including the triple quotes at the end, by extra 2 spaces, you can see that that doesn't actually affect the output. Now, the next productivity language feature in Java 14 on our list are records. Records, again, are a preview feature in Java 14 and 15. There were some changes between the releases too. Usually, preview features go through 2 release cycles of feedback, so likely this will be a permanent feature in Java 16. Like pattern matching, it hasn't been enabled by default in the early access builds yet, or listed with this target officially, but it has been noted on the mailing list, so it's very likely. Records are a really nice feature that really can change the way we code. They basically provide compact syntax for declaring classes for holding immutable data. And the goal really is to make Java a little less verbose, which is nice. One big source of boilerplate in Java are data classes. If you just want to write a simple POJO, DTO, or Java bean, you have to write a lot of boilerplate, right? Constructors, accessors, equals, hash code, toString, that sort of thing. As developers, we don't like doing that, hence the success of libraries like Lombok. And sure, IDEs can help us too. They can generate all of this, which helps us write code, but it doesn't really help us read code, which is even more important. It's a known fact that we spend a lot more time reading code than writing it. Plus, we often read code outside of an IDE, right? For example, on GitHub, where it's even harder to skim through this kind of boilerplate. It would be nice if something like this was supported by the language directly, and that's exactly what records are. Records are a new kind of type declaration in Java. Similarly to enums, they're essentially restricted classes. A record has a name. Let's try to create one here. It has a state description declaring its components. Let's say something like this. I'm just going to model a simple tuple here. And optionally, it also has a body. So let's just create an empty one here. And even though this is very compact, records get a lot of additional functionality automatically. If I try to, for example, instantiate my tuple here, let's say something like this, and let's call it X, you can see that we do actually get a constructor. It's a constructor with the signature, as you would expect, matching the state description, and it initializes the fields correctly from the corresponding arguments here. There's a lot of other stuff too. If we take a look here, you can see that we have a private final field for each component of the state description and a public accessor for each of them with the same name and type. And we can try calling one of them here. Notice that we only have reads, no writes, because records are immutable. And notice that the accessors are named like their components. That means it's even more important now to pick good names because they directly become your API. We also have a few other methods here, like equals, hashcode, toString, and they behave pretty much as you would expect. If I call toString here, for example, you can see that I get a pretty reasonable string representation of this object. By the way this is implemented is through an abstract class called record, which declares abstract equals, hashcode, and toString methods. This class is an implicit superclass of all the records, so kind of like object is for all the objects. Now, in order to make this work, there are restrictions on records. And essentially, all these restrictions have to do with two things: keeping them immutable and not creating additional instance state. They're just data. The state is given completely by the state description. So what does that mean in practice? Well, records, for example, cannot extend a class. If I try to do something like this, you can see that this will not work kind of on principle. And the reason this is not allowed is because classes create instance state, and we don't want that in records. You can, of course, implement an interface because that does not create an instance state. So if I did something like this, implements, let's say, serializable, you can see that this works just fine. You also cannot declare instance fields other than the components themselves. For example, if I try to go back here and add an instance field here, this will simply not compile because that's instance state. You can, however, declare static fields, as it tells you here. If I make this static, you can see this now works as expected because static fields are not instance state. So we saw that records cannot extend classes, but they also cannot be extended themselves. You don't want to change the state of a record by another class later. In other words, they're implicitly final and cannot be abstract. If I try to go back here and make this an abstract record, you can see, again, does not work. The components are also implicitly final to achieve immutability. We saw we only had read accessors there, of course, but even if you try to change it internally, it wouldn't work. If I try to modify my record here, and let's remove the abstract here as well, I can add a new method maybe, just something simple, void update, and inside I'll try to assign to my component here, and you can see that this doesn't work. By the way, this is just plain shallow immutability. What records do in the background is really just create final fields. So if your components had eternal states, for example, they're a date or a collection, you wouldn't be able to change the reference, but you would be able to modify their state, for example, by adding elements to the collection. In other words, it's just plain final here. There's no, fancy immutability. And otherwise, records behave pretty much like normal classes. We saw that you can add methods. You can, of course, add static initializers or constructors too. One interesting case here is the canonical constructor, of course, the one that records get automatically, where the arguments match the state description. like we saw. In that case, you can actually declare this kind of constructor explicitly, but you can still avoid a lot of boilerplate. So if I wanted to create such explicit constructor, I can just write it like this. And let's simulate some validation performed here. Let's just print that we're validating. So notice a couple of things here. We didn't have to specify the brackets and the parameters for this constructor. In this case, it's assumed that it matches the state description. And we didn't have to initialize the components. This gets done automatically. Not only we don't have to, we actually can't. This was possible in Java 14, but as of Java 15, it's a compile time error. By the way, there's another new constraint as of Java 15, and that has to do with the visibility of the canonical constructor. In Java 14, the constructor had to be public, which of course can sometimes be impractical. As of Java 15, the implicit constructor gets the same access modifier as the record class. If you declare it explicitly, it needs a modifier that gives it as much access as the class itself or more. And now we can try to test this constructor. Let's just create a new instance of this class here, and let's call this X, and you can see that this works, and it indeed is using my constructor. Also notice that the fields were correctly initialized, even though I didn't actually initialize them in the constructor. They just got initialized implicitly from the state description. What this allows us to do is maybe have a quick and simple constructor that just does validation of components, and if no exception is thrown, it will auto-initialize correctly, which is pretty cool. Similarly to nested and local classes, we can also have nested and even local records. So small records inside methods. If I go back to my record here, I can just use the constructor as a sample method, and I can create a new record. Let's call it helper. Let's give it some state, and you can see that this also compiles. And since the whole purpose of records is to immutably hold data, this makes them an ideal construct for storing intermediate values. There's a small but important difference between local records and normal classes, though. Normal local classes can access variables of the enclosing method. However, local records are implicitly static. In other words, their own methods cannot access any variables from the enclosing method. And the reason for that is that this enclosing instance would add state to our records. And like we said several times before, we don't want some sneaky state leaking into our records. Similarly to classes, we can also apply annotations in records as well as their components. We can, for example, go back to one of our previous records. Let's just take a simpler one, maybe just this one here, just so that I don't have to type that much. And we can add an annotation here. Let's just make it deprecated, and you can see that this works. And like other classes, records can be generic too. I can parameterize it here, and then, for example, use that as the type of one of the elements of my state. By the way, at this point, you're probably noticing that even though I'm modeling a tuple using a record here, records are actually a lot more than basic tuples, right? Their attributes have names. You have constructors that can validate the state and enforce invariance. So this concept is more than what we would just need to have tuples in Java. They're also not the same as value types. Both value types and records are essentially immutable data classes with restrictions on how they can be extended, but value types are about enabling flat and dense layout of objects in memory in exchange for giving up object identity. Records, on the other hand, are more about concise syntax and still have identity. One final thing to note here, because we now have this new form of a class, essentially, the reflection API was also enhanced to accommodate this. For example, we can test whether a class is a record. We can do that easily by calling its record here, which is similar to its enum. We can do other things. We can, for example, extract the components just by calling it record components. And you can see that this returns an array of the actual components that we have here. And we can extract all sorts of information from them. If I try to get access, for example, to the first component in my list, I can extract its name. I can extract its type. I can extract its accessor. And a lot of other things, things like annotations, pretty much everything that you would expect from reflection. This concludes records and brings us to the final productivity language feature in Java, again out of Project Hamper. And that feature are sealed classes and interfaces. Sealed classes and interfaces are classes and interfaces that restrict which other classes or interfaces may extend or implement them. By the way, this is not a Java 14 feature, not even in preview. This is a brand new preview as of Java 15, so likely something that won't be finalized before Java 17. So why do we need something like this? Well, restricting a set of subclasses is a design goal that we encounter in APIs relatively frequently, yet our current tools are pretty limited. We can either make a class final, in which case it can have no subclasses, or we can make it package private, in which case it can have subclasses, but only in the same package. And this might be enough for many cases, especially if we're using inheritance as a means of reusing code. But it's often not enough when we're using inheritance for domain modeling options in a certain domain. For example, let's say we're developing a library for processing text in different formats. So we make a class to represent format, and let's make it abstract class format. And this is going to be our format representation. Now our library handles different formats differently, so we make more classes. We make a class, let's say YAML, which is a format. And let's make another one. Let's call it XML. Now, these are the only formats we want to handle in our library. We're not interested in handling or defending against other unknown subclasses, some custom formats someone else develops. It's too complex to be flexible enough to accommodate all possible formats. If we could restrict this, that would make maintenance easier too. For example, when we change things later, we wouldn't need to worry about maintaining all the possible invariants in any random implementation someone might have against our API. But in Java, it's an all or nothing kind of approach. If format can be extended at all, it can be extended by any number of classes. If we want format to be widely accessible because it's an important abstraction for users of our library, it has to be widely extensible as well, even by subclasses not known by the author. So it would be helpful if, as the authors of our library, we could say both to the reader and the compiler, hey, this class is co-developed with these other subclasses, and then we declare a class hierarchy that is not open for extension by arbitrary classes, only within this defined tree. And that's exactly what sealed classes are about. To seal a class, we need to do two things. We need to add a sealed modifier, which we can do here. Let's seal this one. And we need to add a permits clause to specify the class is allowed to extend this class. So we can say, okay, permits YAML and XML. And now if someone tries to create another unauthorized format, they won't be able to. If I go back here and create a new format, what's a good example? Plain text maybe, this will not be allowed. Now, there are a few rules to obey here, and the first rule has to do with location. Permitted classes must be located near the superclass. Near in this context means in the same module or package if the module is unnamed. If they are in different packages, you can qualify their names in the declaration of the superclass. A special case of this is having subclasses in the same source file as the sealed class, which is actually a very useful pattern when you have a small number of small sort of one-off classes. In that case, you don't have to specify the permits clause. The compiler will infer it automatically by scanning the file and seeing what classes extend your sealed class. This single file is the only case when you can use the sealed modifier without the permits clause. Otherwise, you need to specify both. Which brings us to the second rule. When you use the permits clause, you need to make sure every subclass directly extends the superclass. You can't list it and then have it not extend the superclass. Rule number 3, every permitted subclass must be declared with a modifier that determines how it continues with the sealing that its parent started. You saw that when I declared this YAML and XML classes, I used the final modifier. That wasn't by chance. It actually would not compile without the modifier. In our case, I was saying that sealing ends with YAML and XML, nothing can extend them. And it's not the only option. Alternatively, I could have used the sealed modifier again and extend the hierarchy by declaring further subclasses of YAML or XML that are also allowed. And we can actually try that here. If I go back to my YAML, I can say, okay, instead of final, this is actually now a sealed class that extends format and permits, let's say, JSON. YAML is a superset of JSON, right? And the compiler can deal with this kind of transitive dependencies, of course. And I said it wouldn't work without any modifier, but that doesn't mean that there isn't a way to keep it open. It just means that as the author, you need to be explicit about which of your subclasses you want to designate as an extension point. And then, you can say that they allow for extension by other unknown subclasses. The way to do this is by using the non-sealed keyword. So if I wanted to accomplish this with YAML, just make it kind of openly extensible, but still a subclass of my sealed format, I would have to call it non-sealed here. And then, of course, I don't need the permits clause afterwards. and that works just fine. By the way, these modifiers are mutually exclusive. So you can't make something final and sealed, or final and non-sealed, or sealed and non-sealed. Final basically means strictly sealed with no permitted subclasses. So this is one thing that could be potentially confusing. Sealing without the permits clause is for multiple subclasses in the same file, not for allowing extensions. That's what final is for. Abstract modifier works with sealing as you would expect. So sealed classes can be abstract, as we saw. Of course, that's actually a very common scenario. Non-sealed classes can be abstract as well. Why not? If I take a look at my YAML class, I can make it abstract here, and it's all good. Final classes cannot be abstract for obvious reasons, right? What would that even mean? And finally, I just want to mention that although I have been using classes in my examples, sealing behaves the exact same way for interfaces too. As in, interfaces can also be sealed, and we can permit implementations and sub-interfaces. Sealed classes as a feature tie nicely, or will tie nicely, into several other features that we've gone over today, including pattern matching, switch expressions, and records. Pattern matching and switch expressions haven't been fully integrated yet, but the plan is to do so in a future Java release. The boilerplate issue this will solve is the fact that when we use inheritance for domain modeling, and we want to handle different subclasses differently, like YAML and XML in our format example, that handling often translates to methods that have a bunch of if statements with instanceof checks and a catch-all. We can imagine, for example, a process text method, which would say, hey, if format is an instance of YAML, process it like this. If format is an instance of XML, process it like this. Otherwise, do this. And if we'll have a lot of subclasses, this not only gets unwieldy, but it's prone to errors too. Because if we add a new subclass, it's not like the compiler can alert us to the methods where we need to add the logic, because the superclass is universally extensible, right? So we always have this catch-all, which would simply kick in. However, with sealed classes, we don't need these catch-alls because we enumerate the extension points. So the compiler will alert us when we add a new one. And that's very, very useful. On top of that, we already have some pattern matching on instanceof, and if we extend it to switch, we'll be able to have very concise methods for handling different formats, for example. We can just switch on formats, right, and list subclasses as cases in our switch with pattern matching out of the box. In other words, in a future Java release, we might be able to do something like this. I'll just create an instance of a format to use here, and I will do a switch on this format, and then I could say things like, okay, if this is YAML, and let's do pattern matching here, do something on this YAML. If this is XML, do something else with this X. And of course, this doesn't work now. This is a future feature, but maybe one day. Sealing also works well with records. In fact, because records are implicitly final, it's actually very concise. If we create an interface to permit a record tuple that we used before, let's bring back the tuple. In fact, here we have our tuple here. So we can create an interface, and let's make it sealed. Let's say sealed interface would be a good example. Data tuple is a data structure, right? So we can do something like this. And then we need to modify our record to actually implement our interface. And you can see that this works nice. It's very nice and clear, no modifiers necessary. And the reason I wanted to mention this integration of sealed classes and records explicitly is because together they provide what's sometimes called algebraic data types. Algebraic data types are a kind of composite types. In other words, types formed by combining other types. The two main forms of algebraic types are product types and sum types. Product types combine multiple values of different types into one, so effectively they are records. Sum types have values from either one type or the other type, so effectively they are sealed classes. So that's a nice kind of alternative way of viewing records and sealed classes as complementary constructs. Records can be viewed as and between types, and sealed classes can be viewed as or between types in a way. Just a final note to wrap up. Similarly to how the reflection API was modified for records, it was also modified for sealed classes. So we can, for example, take our sealed class here and test through reflection if this is actually sealed. We can extract permitted subclasses, and this gives us an array. Of course, I only have one now, so if I just access it, I can take a look at, for example, display name, and you can see that this is my subclass here. In the last few minutes, we'll briefly take a look at new APIs in Java 14, starting with the Flight Recorder API. You may have heard of Flight Recorder because it was pretty successfully marketed and its functionality was delivered over several releases of Java. Java 7 sort of provided the basis for it. It introduced infrastructure for tracing across all subcomponents of the JVM and printing this information to standard output. This was done in the form of timestamped events like garbage collection or method compilation, things like this. Java 11 then introduced the Flight Recorder as basically a monitoring tool for Java. So it was a framework for recording events from applications, the JVM, and the operating system, and you can even use this to monitor other processes. New events were added as well. These would be things like memory, CPU load, process information from the OS, garbage collector configuration, compiler configuration, memory leaks from the JVM, I/O, exceptions, and errors from the JDK libraries. Events get recorded to a file, which you can save and attach to a bug report or use it to analyze a failure that occurred in production, post-mortem. And these files where you store the events usually have the extension JFR and they're binary. So their format might change, but that doesn't really matter because we have stable APIs to interact with them. What Java 14 did is it extended this even further and added event streaming for continuous monitoring of your application. So you no longer need to manually start a recording, stop it, save it to a file, and parse it. You can just subscribe to events asynchronously and stream the data directly without storing it in a recording file. And we can demonstrate it with a very simple example. I'm just going to create a new recording stream here, and let's call this RS. And now I'm going to create an event that I want to monitor. Let's say I'm going to take a look at CPU load. And now I'm going to enable this event on my stream. And because this is a sort of a continuous event, I'm going to sample it with a period of, let's say, 1 second. So something like this. And now I need to provide the handler for my event. So on event, what I want to do, I'm going to just basically print out the event. That should be enough. So just a quick method reference here. And finally, I should be able to start my recording stream. And now every second we get CPU load statistics, which is pretty cool, and it was very easy to accomplish. There are many other events available kind of out of the box as well. We can take a look here. If I obtain an instance of Flight Recorder, at Flight Recorder here, I can see what the event types are available. This actually returns a list, so I'm going to stream it and then extract some information from this. Maybe for each event, give me the name of the event, and then let's just print it out. Quick method reference again. Something like this. And you can see there are quite a few events available here for all sorts of things, really. So that's Flight Recorder, just a nice little convenient API for tracing here. Finally, let's briefly touch on the topic of free memory access. Free memory access API is again a feature in incubation in both Java 14 and 15, with quite a few revisions between the two releases actually still a subject to change. But as we said before, even though not pinned yet, likely to be finalized in Java 16. This feature comes out of Project Panama, which focuses on making the JVM and non-Java APIs more interoperable. As the name suggests, this is an API for accessing memory outside of the Java heap. The main reason why we want to do such a thing is performance, particularly avoiding garbage collection or sharing memory access across processes, that sort of thing. This might sound pretty niche, but it's actually quite common. There are quite a few pieces of software that already take advantage of such functionality. In fact, many of us, if not most of us, probably use such software pretty regularly. There are existing constructs in the JDK that allow us to do this, but they're not very good. We have the byte buffer API, for example, which is an old API back from Java 1.4, and this API allows us to create direct byte buffers allocated off heap directly from Java. This doesn't work very well and has size limitations as well as garbage collection issues. We also have Java native interface, JNI, which allows us to call native applications and as such also access memory. But it requires us to write C code, and it is very slow because basically we're constantly translating between Java and native. And finally, we have the infamous sun misc unsafe. And that's what most tools are using because it's very fast. This is an unsupported API, and as the name suggests, it is unsafe. You can access any memory location, so you can potentially break your own JVM if you're not careful. So we need something better. And 40 Memory Access API is our first attempt at that. The API introduces 3 abstractions. There's memory segment, which models a continuous region of memory. There's memory address, which is a location within a given memory segment. And there's memory layout, which is a way to define the layout of a memory segment. And here's how it works. I can allocate a memory segment. Let's say just something memory segment, allocate native, let's just say 100 bytes, and let's call this segment. Then I can obtain a memory address within this segment. The easiest way to do this is by calling segment base address, and let's call this address. So you can see that this is the base within my segment. It's offset 0. To access the underlying data, we need to use a memory access var handle. Var handles in Java are basically just a typed reference to a variable, or in our case, reference to a component of an off-heap data structure. I can obtain such var handle from memory handles. So if I just call memory handles var handle, and this needs a class and byte order, let's just use something simple. I'm just going to use integer, and I'm just going to keep the default byte order just like this, and let's call this handle. And now I can use this handle to write something to my segment. So I'm going to write something to the base address, some sort of an int, let's say 100. And now we can see if this works. I can read from this address. So let's just call get, and you can see that this indeed returns 100. This, of course, is not a very practical way of accessing memory. It's basically purely by offsetting a memory segment. Most often, you would want to organize the data in some layout, which is what the memory layout and memory layouts classes are for. Memory layouts is basically a bag of convenience predefined layouts, sort of building blocks that Java comes with out of the box. We can take a look here, memory layouts. You can see that there's quite a few of them. These are mostly simple value layout models for basic data types like integer or double. So each of these has a predefined size, which is the same as the corresponding type, and the byte order. If I want something more complex, the way to do it is by using memory layout without the S, which is an interface that memory layouts implement. And this allows us to construct more complex layouts from the building blocks. For example, I can create a sequence layout, which is a repetition of a given layout. I can just call of sequence, and let's say I want 25 times in sequence the layout of, let's say, double. And that's what I'm getting here. And of course, you can combine layouts in many different ways and even make your own, but that's beyond the scope of this talk. So that's it from me. I hope you found this talk useful. If you want to get in touch, here's my Twitter handle in the corner here. And otherwise, thank you and enjoy the rest of the conference.